Welcome to another educational video brought to you by Andover Corporation. Today I want to answer the question, what is a long wave pass? Now it sounds like a simple question, but there's actually a lot going on. So let's begin and let's talk about it. A long wave pass is an edge filter that rejects the lower wavelengths of light and passes the longer wavelengths of light. That's why it's called long wave pass, passing the longer wavelengths. Typically, a long wave pass is specified by its 50% point with some sort of tolerance in wavelength, or it could be specified as its 5% point, which is more familiar with infrared long wave passes. Now, this region right here is called the transition region, where you're going from high T to low. A lot of the times, the specification here is called slope. Your slope could be defined as 5% to 80%, or 10% to 80%. And occasionally it's specified from going from your 80% point down to an optical density. That means going from, say, 80% up here to, say, OD3 within a certain amount. If there's a specific wavelength of light in this area that you must have locked to OD3, OD4, optical density, then you need to be down by that point, and that's what's specified. So this transition region, as you make it steeper and steeper, you need more and more layers. More and more layers means more coating, more time. That can make your filter more expensive. That's a cost driver. Sometimes it's necessary, but just be wary of specifying well beyond what you need. Occasionally, requests will come in where you will have a specification from 400 to 700, where you want a certain blocking, and then 700 to 1100 nanometers, where you want the transmission. Now you'll notice no transition region was specified, so it'll be hard to determine what's more important, blocking or transmission. So when specifying a filter, it's important to give a 50% point or give up and down points that allow for a transition region. It's more realistic. Specifying a filter that comes up and immediately is a straight line that way isn't realistic. In theory, it looks great, but it's not realistic. So a long wave pass filter can be used in a different way as well. It could just be not the transmitted light that you're using. You may want to use the rejected light as well in reflection. So if this light is going to be used in reflection, and then you have your transmitted light, that is what we like to call dichroic. Occasionally they're called beam splitters as well, or beam combiners, things like that. So this reflected light and transmitted light can then be used. To make it more complicated, dichroics are more specifically used at angles. So if this is the curve at a 0 degree angle of incident, if we start to look at this curve at 45 degrees, which is a typical angle to use, this is what happens. You'll get a downward shift in wavelength, and you'll get a hitch, is what we call it right there. And this transition region will widen. The reason for that is as you go to an angle, you're going to have separation of the polarizations. So you'll see that here will be the S polarized light, and here will be the P polarized light. So random polarization will show this hitch, widening the transition zone. So if you're asking for a long wave pass or a dichroic at 45 degrees with a very small transition zone, you're requiring a very difficult filter. Now, it's possible, it just makes your filter more difficult to produce. So these 45-degree dichroics can be used in prisms. And those would be dichroic beam splitters or cube beam splitters, where you have a prism and light will come in this. And that would be 45-degree angle dichroic. That's very popular. So I hope this has been some help to you, describing long wave passes and maybe some of the cost drivers. And remember, adding angle, adding steepness, and also increasing optical density of your rejection are all cost drivers. So make sure you know what long wave pass you want for your application.